Section 13.1.25. An engineer wants to know if the mean strengths of 3 different concrete mix designs differ significantly. He randomly selects 9 cylinders that measure 6 inches in diameter and 12 inches in height, in which mixture A is poured, 9 cylinders of mixture B, and 9 cylinders of mixture C. Now, after 28 days, he measures the strength in pounds per square inch of the cylinders. The results are presented in the accompanying table over here. Now, we want to state the null and the alternative hypothesis. Now, the hypothesis regarding K population means are given below. So, we have the null, which is the mean of mixture A, which is equal to the mean of mixture B, which is equal to the mean of mixture C. The alternative is that at least one of the means is different. Okay, now we want to be able to explain why we cannot use one-way ANOVA to test these hypotheses. So, first and foremost, the requirements of a one-way ANOVA test are given below. There are K simple random samples, 1 from each of the K populations. The K samples are independent of each other, and that is the subjects in one group cannot be related in any way to subjects in the second group. The populations are normally distributed. The populations have the same variance, that is, each treatment group has population variance. According to the problem statement, the samples are random and independent of each other. Now, we want to draw normal probability plots and determine the samples are given from populations that are normally distributed. Now, recall that if the normal probability plot is roughly linear and all the data lie within the bounds, there is reason to believe the data come from a population that is approximately normal. So if we come in here, okay, and we want to find the normal probability plot, so we're going to select the QQ plot. We're going to select mixture A, mixture B, and mixture C, and then take a look at the correlation statistic. Okay, we can see here is for mixture A. So if I scroll down here, there is the graph of mixture A that has a correlation of 0.982, so therefore that is approximately normal. If we take a look at the next one to the right here, we're going to see that mixture B also has a correlation of 0.988, and therefore that is approximately normal. And then if we take a look at the last one, for mixture C, we have an approximately normal distribution where the correlation is 0.986. Okay, now, since the normal probability plots are roughly linear and all the data lie within the bounds, the normal probability plots indicate that data come from a population that is approximately normal. Okay, now, the one-way ANOVA procedures may be used provided that the largest sample standard deviation is no more than twice the smallest sample standard deviation. So we need to come back in here in the stat crunch. We're going to go to stat, summary stats, and then find the standard deviation of all 3 of these mixtures. So we take the standard deviation, and then we can see what we get there for this summary of stats. So I copied the summary of stats here, and you can see here that mixture A has a standard deviation of 115.4, mixture B has a standard deviation of 381.3, and mixture C has a standard deviation of 191.7. Now, since the standard deviation for mixture B is more than 2 times larger than the standard deviation for mixture A, meaning that standard deviation for B is 381.3, it's greater than 2 times the smallest one, which is 115.4, the requirement of equal population variances is not satisfied. Therefore, one-way ANOVA cannot be used to test these hypotheses.